Welcome to the second half of Orderability of Dehn filling. Recall from last time, we talked about what is the group PSL2R tilde and how to use PSL2R tilde representations of a fundamental group to show the left orderability of the fundamental group. And then we talked about why we need Dehn surgery of the knot complement. And then we introduced the translation number of elements in PSL2R tilde and how to classify PSL2R tilde representations of the knot complement into elliptic, hyperbolic, parabolic, and central according to its restriction to the boundary. So in the second half of my talk, first I'm going to tell you how to parameterize PSL2R tilde representations of a knot complement. First, let's look at the PSL2R tilde representations of the knot complement M. That's hyperelliptic, parabolic, or central when restricted to the boundary. This method was first introduced by Kohler and Dunfield. Let PE sub G tilde of M be the set of PSL2R tilde representations of M that's elliptic, parabolic, or central when restricted to the boundary. Remember, in the first part of the talk, we said that for elliptic elements in PSL2R tilde, the translation number can be any real number. It measures the amount of translation on the real line, so it does not lose any information about the translation. Therefore, we can use translation numbers to parameterize a PSL2R tilde representation that's elliptic when restricted to the boundary. For parabolic elements, the translation number will lose some information, but since we do not really care about representations that are parabolic or central and restricted to the boundary, so we don't need to worry about them. Okay. So for a PSL2R tilde representation, we map it to a point on the real plane, where the first coordinate is the translation number of rho tilde of the meridian, and the second coordinate is the translation number of rho tilde of the longitude. So these coordinates keep track of the action of the meridian and the action of the longitude on the real line. Therefore, if you have an element of the fundamental group of the boundary, which is represented by a curve of slope, say P over Q on the boundary, then you can use these coordinates to recover the action of this element on the real line. And we will call the closure of the image of this map the translation extension locus of M, and it's denoted by EL sub G tilde of M. So the translation extension locus is just a subset of the real plane. And in fact, it has even better property. The theorem by Kohler and Dunfield says that the translation extension locus is in fact a graph in the plane. It's a locally finite union of analytic arcs and isolated points. And moreover, it's invariant under translation by integers in the x direction. So it has a repetitive pattern in the x direction, but it's not invariant under translation in the y direction. So now we are left with the hyperbolic case. If we try to parameterize them as we did in the previous ellipse case using translation numbers, then we will run into problem. This is because for hyperbolic elements in PSL2R tilde, the translation number can only be integers, and therefore we'll lose too much information. Then we need to find a way to remedy the information. So let rho tilde be a PSL2R tilde representation of M, and let rho be its projection to PSL2R, and then the image of the meridian and longitude under rho are two matrices in PSL2R, and moreover, they commute with each other. Therefore, we can look at their eigenvalues corresponding to the same eigenvector. And turns out that their eigenvalues are exactly the information we need. So we can do similar things as in the previous slide. Let PG sub G tilde of M be the subset of PSL2R tilde representations of M whose restriction to the boundary is either hyperbolic, parabolic, or central. And again, the parabolic and central cases are not so important. We will only care about the hyperbolic case. The closure of the image of this map is called the holonomic extension locus of M, and is denoted by HL sub G tilde of M. So you can think of the holonomic extension locus as living in Z cross Z planes. And these planes are indexed by the integers I and j, which are the translation number of the meridian and translation number of the longitude. And we will denote the intersection of the holonomic extension locus with the ij's plane as hij. And it turns out that the holonomic extension locus is actually a locally finite union of analytic arcs and isolated points. So in fact, each hij is a graph inside a plane. And moreover, it has the property that if the j index, if the translation number of the longitude are the same, then the two different graphs in different planes are identical. Now let me show you some pictures as I promised. Let's take a look at the 732 bridge knot. The top left picture is the translation extension locus of the 732 bridge knot. We can see these curves belong to the translation extension locus. And we can see the repetitive pattern in the x direction of the curves. And also notice that this graph is invariant under reflection about the origin. The top right picture is HI0 of the holonomic extension locus of the 732 bridge knot. And these two curves belong to the holonomic extension locus, and they continue to infinity. And we can also see that this graph is invariant under reflection about the origin. And this subscript 0 means that for every representation corresponding to a point on the curve, the translation number of the longitude under the representation is 0. Okay. The bottom left picture is HI1 of the holonomic extension locus of the 732 bridge knot. Okay, so this curve belongs to the HI1, and the translation number of the longitude is 1. And the bottom right picture is HI minus 1 of the holonomic extension locus. Yeah, so the translation number of the longitude is minus 1. Okay. If the translation number of the longitude is greater than 1 or smaller than minus 1, then there is no arc of the holonomic extension locus living in that plane. So these 3 pictures compose the entire holonomic extension locus of the 7th-3 two-bridge knot. Next, I will talk about the applications of translation extension locus and holonomic extension locus of a knot complement. Let L sub r be a straight line of slope minus r through the origin in R2. Be careful, it's this minus sign here. Okay. Then this following lemma by Cooler and Dunville says that if L sub r meets the translation extension locus at a non-zero point, which is not parabolic or ideal, then the Dehn filling of M along slope r is orderable. I need to explain what ideal means. Remember, in the definition of translation extension locus, we are taking the closure of the image of this parametrization. So ideal point means that this point does not live in the image of this map. It only lives in the closure. So it does not come from representation. Similarly, for the holonomic extension locus, we have this following theorem. So if L sub r intersects H00 of the holonomic extension locus of M at a non-zero point, which is not parabolic or ideal, then the Dehn filling of M along a curve of slope r is orderable. Here, the ideal also means that in the definition of holonomic extension locus, the point does not belong to the image of the parametrization. This point, the ideal point, only lives in the closure of the image of the map. So it does not come from a representation. Okay, come back. The translation number of the longitude being 0 is very important. For other sheets of the holonomic extension locus with non-zero translation number of the longitude, we do not have the theorem. Let's look at the pictures again. First, let's take a look at the translation extension locus of the 7-3 two-bridge knot complement. Every point on the curves of the translation extension locus comes from a PSL to R2 representation of the knot complement such that it's elliptic when restricted to the boundary. We pick one point, say here, and then this point comes from a PSL to R2 representation of the knot complement. Say the representation is rho tilde. Suppose this point has slope minus r. Then we take a look at the curve of slope r on the boundary of M. Then this curve of slope r corresponds to an element gamma in the fundamental group of the boundary of M. One boundary. If we compute the translation number of gamma, then we will find that the translation number of gamma under the representation rho tilde is actually 0. So we know that rho tilde applied to gamma is identity. So the kernel vanishes. Therefore, rho tilde now induces a PSL2R tilde representation of the Dehn filling of the knot complement with slope R. Therefore, we know Dehn filling of the knot complement with slope R is left orderable. And this is how the translation extension locus works. The case for holonomic extension locus is similar. If we look at the H00 of the holonomic extension locus of the 732 bridge knot, then every point on curves of the holonomic extension locus comes from a PSL2R tilde representation of the knot complement, and it's hyperbolic when restricted to the boundary. Let's pick a point, say here, then it comes from a PSL2R tilde representation of the knot complement. Say it's rho tilde, and suppose the slope of this point is minus R. Then if we apply similar procedures, we will see that rho tilde induces a PSL2R tilde representation of the Dehn filling of the knot complement of slope R. And therefore, we know that Dehn filling of the knot complement of slope R is orderable. Let's go back to the translation extension locus and look at all the curves in the translation extension locus. If we intersect the curves with straight lines through the origin, you can see that straight line of slope from minus 1 to positive infinity will intersect. And therefore, if we apply this lemma, we know that Dehn filling of the 732 bridge knot complement of slope from minus infinity to 1 will be orderable. And similar here for the holonomic extension locus. We intersect with straight lines through the origin, and then we know Dehn filling of slope from 0 to positive 4 will be orderable. And therefore, these two pictures in total tells you that Dehn filling of the 732 bridge knot complement of slope from minus infinity to 4 will be orderable. We could run more examples with two bridge knots. For example, this is the 2310 two bridge knot, which is 8-6 in Rolfson's table. The picture on the left is the translation extension locus of 8-6. In translation extension locus, this pattern is going to repeat in the x direction, but I only kept the fundamental domain for simplicity. And the picture on the right is the holonomic extension locus of 8-6. Okay. If we apply the previous two lemmas, then we can intersect the curves with straight lines through the origin, and we will see that Dehn filling of the A6 complement of slope from positive infinity to -1 is orderable. And in the holonomic extension locus, we also intersect the curves with straight lines through the origin. And we know that there should exist an interval containing the origin such that for every slope in that interval, Dehn filling along that slope is orderable. After running lots of examples with two bridge knots, we found out that this pattern of translation extension locus and holonomic extension locus hold for all two bridge knots. And to check that, we tested this special class of two bridge knots, which we called the double twist knot. So the name comes from the presentation of the knot where there are two twisted regions. The reason why we chose this special class of two bridge knot is the representation variety and character variety of the double twist knots are fairly easy to compute, so we can compute directly. And by applying translation extension locus and holonomic extension locus and computing the character variety and representation variety, we prove the following theorem. So the theorem says that for the double twist knots, there is an interval such that for every slope in that interval, Dehn filling along that slope is orderable. And we believe that these techniques could be applied to more general classes of knots. So this is the end of my talk. Thanks for listening.